When you see an oil refinery, it's like looking at a sprawling industrial city, just this ocean of volatile chemicals and explosive energy. And they're absolutely essential to our modern world, right? But they're operating on the absolute razor's edge of disaster. So the big question is, how do we manage that incredible risk every single day? Let's dive in.
I mean, just look at this. This is the Texas City Refinery. It is a colossal network of pipes and tanks and towers, and it processes hundreds of thousands of barrels of crude oil every single day. The amount of flammable material packed into one place here, it's just staggering.
So that brings us right back to our central question. How on earth do you keep a place like this from blowing up? Well, it's not just one thing. It's a whole series of complex, overlapping layers of protection, all designed to contain the almost unimaginable force of the chemicals themselves. To really get the solutions, you first have to understand the monster they're trying to contain. There's this one single, greatest threat that every single safety system in a refinery is designed to prevent. It has a name, and that name is a BLEVE.
BLEVE. It stands for a boiling liquid expanding vapor explosion. Now here's the thing that might surprise you. This is a physical explosion, not necessarily a chemical one. You don't even need something flammable for it to happen. All that immense energy comes from a sudden, violent change from a liquid to a gas.
So how's it work? It's a terrifyingly simple three-step process. First, you've got a liquid. Could be propane, could even be water, stored under a whole lot of pressure at a temperature way, way above where it would normally boil. Second, the tank fails. It just ruptures, and all that pressure is gone in an instant. Third, without that pressure holding it down, the superheated liquid explosively boils, flashing into vapor and expanding over 1,000 times in volume in just a fraction of a second.
The result? It's pure devastation. We are talking about a blast wave that can level buildings, and it can launch huge, multi-ton chunks of that tank like they're rockets. And if that rapidly expanding cloud of vapor happens to be flammable, like gasoline, and it finds an ignition source, then you get a truly catastrophic fireball. Okay, so with stakes that high, preventing a BLEVE is, the absolute #1 priority. The very first line of defense is all about being proactive. It's about using chemistry to make it impossible for an explosion to even happen in the first place, by taking away one of the key ingredients.
And that brings us to our first layer of defense. You just get rid of the air. Specifically, you get rid of the oxygen. It's a process, and it's known as inerting.
The idea behind inerting is actually brilliantly simple. You just pump an inert or non-reactive gas into a tank or a pipe. This gas physically pushes out or displaces the oxygen. And if you can get that oxygen level below a specific point, it's called the limiting oxygen concentration. Combustion literally cannot happen. You can have all the fuel you want, you can have an ignition source, but without oxygen, there's no fire. Game over.
Now, the two most common gases for this job are nitrogen and carbon dioxide. And as you can see, they've got different pros and cons. Nitrogen is cheap, it's versatile, it gets the job done. But carbon dioxide is way heavier than air, so it's great for forming a thick, protective blanket over liquids. It's also really good at putting out fires that have already started.
Okay, but what if something goes wrong anyway, and pressure starts to build up? That's where our second layer of defense kicks in. This one's reactive. It's designed to handle a crisis as it's happening.
Think about a pressure cooker on your stove. It's got that little valve that jiggles and lets steam out so it doesn't explode. Well, if the pressure inside a refinery tank gets too high, something has to give. And this is the refinery's version of that little jiggling valve.
This is a flare stack. I bet you've seen these burning from the highway and probably thought it was just pollution. But a lot of the time, it's actually a critical safety system doing its job. When a vessel overpressurizes, valves automatically open up, send all that excess flammable gas up this huge stack, and it's burned off safely way up in the air. This prevents a much, much more dangerous explosion down at ground level.
And if you want to see what happens when pressure control fails, just look at this. On the left, that's the raffinate splitter tower at the Texas City Refinery before the 2005 disaster. And on the right, that's what was left after. An uncontrolled release of pressure led to one of the absolute worst industrial accidents in U.S. history. The stakes just could not be higher.
But what if the human operators miss something? What if the normal control systems that run the plant just fail? Well, there's one last line of defense, a silent digital guardian that steps in when everything else has gone wrong.
It's called a Safety Instrumented System, or SIS for short, and the absolute key to the SIS is that word independent.
This is not the same computer system the operators use day to day. The SIS is a completely separate, hardened, dedicated system. It has one job, and only one job: shut things down and get the plant into a safe state if it detects anything dangerous.
It works kind of like a reflex in your body. You've got independent sensors monitoring things like pressure or temperature. If a limit gets crossed, they send a signal to a dedicated computer, the logic solver, which then commands a final element, like a valve, to take immediate action. So, sensor, logic, action. It's simple, it's robust, and it's incredibly reliable.
So we have these amazing layers of defense, right? Inerting the tanks, pressure relief flares, automated shutdowns. So you're probably wondering, how could a disaster like Texas City even happen? Well, it happens when the weaknesses, the small holes in each of those layers of protection, all tragically line up.
So in the morning of March 23, 2005, operators were restarting this raffinate splitter tower. Procedures weren't followed right, and they dangerously overfilled it. Critically, a high-level alarm that should have warned them, it failed. As the liquid inside got hot, it expanded, and it blew open the pressure relief valves. But instead of going to a modern flare, the liquid and vapor were sent to an older-style vent stack, which released this massive low-lying cloud of flammable vapor that quickly found an ignition source.
This is what safety experts call the Swiss cheese model. Think of each layer of defense as a slice of Swiss cheese. Each slice is a good barrier, but it has some random holes in it. A disaster happens on the rare occasion that all the holes in all the slices line up perfectly. And that day, they did. Bad plant layout with trailers too close, a failed alarm, procedures ignored, a supervisor wasn't there, an outdated release system. Any one of these failures by itself might have been okay, but together, they created a direct path to catastrophe.
And this was the result. The explosion absolutely obliterated these temporary office trailers. Every single person who died in the disaster was inside one of these trailers, which, as it turned out, should never have been located so close to a hazardous process unit in the first place.
The Texas City disaster was just a brutal, tragic reminder that safety isn't some static thing you achieve. It's a never-ending battle. A battle against physics, against equipment failure, and, yep, against human error.
15 people went to work that day and never came home. That number isn't just a statistic, it's the real human cost of what happens when those layers of protection fail. Which really leaves us with a final, kind of sobering thought. In these incredibly complex systems, where people and machines have to work together perfectly, is it even possible to design a system that's flawless? To make a piece of Swiss cheese with no holes? Or is the best we can ever hope for just to be constantly, relentlessly vigilant, always searching for those holes before they ever get a chance to align?